So I was just mentioning to the students in here a minute ago that Calvin cycle I find difficult to teach and difficult to get excited about and difficult to get students excited about. So where I want to start this lecture is with this. What is this?
CO2.
Do you know why I like CO2? Because I can still draw it. I never forgot how to draw it. And the reason I never forgot how to draw it is because it's so simple. One carbon double bonded to two individual oxygen molecules. And I remember when I first started learning about organic chemistry, or the existence of the idea of organic chemistry, they said that this is not an organic molecule. Did you ever hear that? What's the definition of an organic molecule?
Contains carbon and hydrogen.
It contains carbon and hydrogen. I think I learned it as it's almost carbon bonded to anything else, but this is not an organic molecule, and that used to really bother me. It's like, well, why not? Why is that not an organic molecule? And now I understand why, because what we consider to be a real organic molecule is, like you said, carbons bonded to hydrogens and possibly other carbons. That's considered organic. And organic molecules are life molecules, right? That's why you have to have a whole two courses in organic molecules. They're life molecules. And having carbon bonded to other carbons and to hydrogens, the reason we care about those, and we have a whole class to study them, is because those molecules contain usable bond energy. Usable bond energy for organisms to use as food, in essence. So we need organic molecules for food as a source of energy, and we need organic molecules also as carbon building blocks. Why is carbon the best for building big molecules?
You can attach 4 bonds to it.
It's got 4 spots. 4 spots for bonds, so you can make big molecules. That's why we care about organic chemistry. Organic chemistry does not include, or let's say CO2 is not considered an organic form of carbon, is because these bonds are not very usable for energy. So this is carbon, let's say in its lowest or its most extreme oxidation state. Have you ever heard that I guess it's a quote from a poem or something like that. Water, water everywhere, and not a drop to drink, about a person that's floating in the ocean and they're thirsting to death. Carbon, carbon everywhere, and not a bit to use, unless organisms can take CO2, which is really abundant, and get that carbon into a usable form. So if you are an organism that can take CO2 that's so abundant on Earth in this oxidized state, and you can convert that carbon into a more usable form, into, ta-da, organic molecules. If you're one of those organisms, we say that you're a primary producer. And plants can do that. Certain microbes can do that. They can fix carbon. So that process of capturing CO2 out of the air and fixing it into organic forms is hugely, hugely important. That's why I keep lecturing on this topic. That's why we insist that you learn about the Calvin cycle. Very, very important. So one thing that needs to stick in your mind is that carbon fixation, the process of pulling CO2 out of the air and getting it into an organic form, that is Calvin cycle in plants. Those go together. I have a few slides on here that were left over from light reactions at one point, but I want to use this one just to review. So up until now, we've been talking about photosynthesis and how it starts with the light reactions. So we have photosystems composed of pigments and proteins that are absorbing light and using that energy from light to boost electrons with their energy. And they use the energy from the electrons to make NADPH, which is reducing power, ATP, which is not shown here, but ATP as an energy source, and oxygen as a waste product. So those are the light reactions. Light reactions are absorbing light, using water, making ATP and NADPH, and releasing oxygen as a waste product. So the products of the light reactions are going to proceed directly into the Calvin cycle. And the Calvin cycle is focused on fixing carbon. This slide you can leave off this year. So these other slides, this one I talked about previously, this one I talked about previously, this one we talked about really, really a lot, or a version of it previously. This one is new, but I'm not going to cover that material this semester. I'm going to go on into Calvin cycle itself. Recall also that in the past they've been called the dark reactions, occasionally the light independent reactions. Calvin cycle is really the best term. But you should know all three, but use in your daily life if you talk about the Calvin cycle in your daily life. Calvin cycle. Skip on past that. So, Calvin cycle is occurring in the stroma. So this is going to be happening in the stroma of the chloroplast. And recall also that the ATP and the NADPH from the light reactions are already there. ATP is produced in the stroma as part of the light reactions, and so is NADPH. So they are already there in the correct location. And the very first step of the Calvin cycle of carbon fixation is getting CO2 to stick. We're going to get CO2 to react with the cell and be fixed. So fixed is implying it's not floating around in the air anymore. It's bound onto another molecule. That's what carbon fixation is in its simplest sense. So CO2 is combined together with a 5-carbon molecule called ribulose. You can also say it ribulose. Ribulose 1,5-bisphosphate. In this class, I do not need you to be able to draw this, okay? I need you to know the name of it. I need you to know that it's involved in the Calvin cycle and that it has 5 carbons. Those are the important things to me in this particular class at Keene. So we're having a 1-carbon molecule, carbon dioxide, attaching onto a 5-carbon molecule called ribulose 1,5-bisphosphate. Or this is also called RUBP. It's often abbreviated that way, RUBP. So RUBP is what is grabbing CO2 and combining with it. Getting those two together is difficult. It's energetically difficult. I'm going to come back to this in just a second. I want to skip ahead to this slide. So getting CO2 together with RUBP is difficult, and the enzyme within plants that does this is called Rubisco. You need to know the name Rubisco and remember forever what it does. So in your group of words that go together with Calvin cycle, CO2, carbon fixation, RUBP, and Rubisco. That's a set of words that go together. And if you can keep those words together in your mind, that will help you on standardized tests and your biology and fat and so on. So Rubisco is an enormous enzyme complex, and in plants it has, it's not eightfold symmetry, but it's a symmetrical molecule with 8 repeating components, whatever that is called geometrically. It's enormous, and it has 8, it's easier to see here, 8 of the large subunit arranged in a ring, and it also has 8 small subunits arranged in a ring. It's symmetrical in this plane, and it's also symmetrical radially around. Rubisco literally crowds the stroma. So if you look at, if you were to isolate stroma from chloroplasts, they have more, stroma has more protein than the usual compartment, and a huge component of it is Rubisco, 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 Rubisco. It is the most abundant is the word I want. It's the most abundant enzyme on Earth. If you ever wonder, I wonder what is the most abundant enzyme on Earth. It's Rubisco. Because every chloroplast, its stroma, is hugely composed of Rubisco, crammed in there, fixing carbon. And Rubisco is what is binding CO2. So each one of its 8 components binds CO2 and gets it to react with RUBP. Another interesting thing about Rubisco is that it is incredibly slow for an enzyme. So each subunit, each of the 8 components, fixes 3 CO2 per second. Does that seem fast? It's super slow for an enzyme. And the reason it's super slow is getting such an oxidized state of carbon to react and attach covalently on the RUBP is a difficult task. So each one has 8 CO2 fixing sites, and the whole thing together could fix 24 CO2s per second. Other enzymes would be working on the rate of 24 million blah blah blahs per second, not 24. So plants need a lot of it. And its name comes from its job. Ribulose 1,5-bisphosphate, that's one of the substrates. And it can act to carboxylate RUBP. That's this process, so adding these two together is carboxylating RUBP. And the other part of its name comes from the fact that it can also oxygenate RUBP. And I want to go ahead and talk about that right now because that becomes important in the upcoming lecture. So 8 active sites. Each active site can bind CO2. Each active site can also bind O2. Why would those two things bind in the same active site?
In case it needs to go backwards.
In case it needs to go backwards. Those of you that are in cell, those are substrates. What about them would make them bind in the same active site? They both have double bonded oxygen with another molecule. This is just smaller. They both have equal charge distribution. They're both symmetrical molecules. They're both small. This is just a little bit smaller. Is it weird to think about these as substrates? If we usually think, oh, there's this little small protein and that's the substrate. These are the substrates to bind in an active site, and they almost have the same chemical properties. Rubisco will bind either one of them. So there are situations where Rubisco will bind oxygen and fix oxygen out of the air, and that's not really what it's needing to be doing. But it binds oxygen instead of CO2 because they have a similar shape. So that's how the oxygenase part of its name comes from. Ribulose 1,5-bisphosphate, joining it to CO2 for the carboxylase, joining it to oxygen for the oxygenase.
Is the point of the Calvin cycle to form sugars?
Yes. From
So-
what? Yeah.
So then why would it like even
Why would
spend
it
time
bind?
to bind O2 if there's not even carbon?
You know why? This is one of the coolest facts on Earth. Because Rubisco is older than oxygen in the air. Rubisco is older than oxygen in the air. It's like the best question. Rubisco is old, old, old. So one of the things I learned today, like when I was background reading from this, is that plants have, 8-fold Rubisco. Microbes have like 2-fold Rubisco. But it's the same general structure of the subunits and the same general operation. So bacteria learned to fix carbon incredibly long ago to do photosynthesis and oxygenic photosynthesis. So Rubisco as a protein machine has existed before an oxygenated atmosphere. It's amazing. So old, so important. It's the most common enzyme on Earth. So old. All right, now let's go back a little bit and talk about the sugar part. Okay, so here's the beginning of carbon fixation in plants. We're taking CO2, forcing it, using Rubisco, to covalently bond with RUBP. So we're adding 1 carbon plus 5. We get this 6-carbon intermediate. And it's like Rubisco has worked so hard to put those together. It's so difficult that this immediately falls apart. The 6-carbon compound falls apart into 2 molecules of phosphoglycerate immediately. Like even before it leaves Rubisco, that 6-carbon intermediate doesn't stay. But Rubisco has done its job of grabbing CO2 out of the air, getting it covalently bound to other carbon, and then you end up immediately with 2 molecules of phosphoglycerate. And again, in this class, I don't need you to draw phosphoglycerate, but I need you to know that it's the early form of fixed carbon in the Calvin cycle. And because the first carbon that we've got fixed out of the air is in the form of 3 carbon molecules. This style of photosynthesis is called C3 photosynthesis. People don't tend to talk about C3 photosynthesis, but they talk about C4 plants that do a different style of photosynthesis. And if your average plant, let's say, your average plant in the world does this style, and it's called C3 photosynthesis because you have 3 carbon intermediates are the first stable form of fixed carbon. And that's the beginning of the carbon cycle, the Calvin cycle. Okay, so here is a depiction of the Calvin cycle. If you did not watch the videos for today, I highly, highly recommend that you go back and watch them. They're not that bad. They're not that bad. They're a really good review. They go through further information about Calvin cycle intermediates. Why can't it be called the carbon cycle? Because that's a whole separate thing, honestly. This is the Calvin cycle. So please do go and watch those. I'm talking about this assuming that you did. If you didn't, that's okay, but you'll need to go back and watch them. So I focus in this class the most on the top, the very beginning of CO2 getting fixed. Rubisco, you should write that in right here. Rubisco is doing this. There's a 6 carbon intermediate that immediately falls apart to phosphoglycerate, which is a 3 carbon molecule. Now, on this side of the Calvin cycle, these steps on this side are using ATP and NADPH let's say to energize the fixed carbon enough so that it can be built into sugar. The goal of this is to make sugars. It is to make organic carbon forms. Those of you that are in cell, we are doing negative delta G reactions on this carbon chain to be able to make the carbon energized enough to join with other carbon to do anabolism. So if you remember, we talked about trying to build new, build bigger is anabolism. It requires energy input or negative delta G reactions to get that to happen. That's what the ATP and NADPH are for. We've caught a carbon out of the air. It's still in a pretty low energy state. So we got it to bind. We've now got 2 3 carbon molecules that are symmetrical. But the carbon that was just captured is still not really energetic enough to be processed further. That's what we're spending ATP and NADPH for. So, spending these, and remember that, where did these come from?
Light reactions.
These are coming from the light reactions. And these are dependent on the light reactions. So it's not that we have to be shining light every single moment that these are spent, but they do depend on light to be formed. So calling these light independent is not quite correct. That's why we need to call it the Calvin cycle. These are coming from the light reactions. They're being spent to provide the energy to build sugar. And that's what I want you to focus on in this class. So what they become then through molecular conversions is glyceraldehyde 3-phosphate.
Why are there so many molecules that are similar to glycolysis? They're all, is this like glycolysis?
Yes.
Of the plant?
This is in glycolysis.
Yeah, all
Yeah.
of those on that side. Right?
Yeah. So the question just now is, why is this so much like glycolysis? It's almost the reverse. So if you think about G3P, super important during glycolysis, and how many things that it could be siphoned out to make. Yeah. So this by itself could feed into glycolysis.
Okay.
Okay, so think of this G3P, and I had told cell biology, if you're going to learn to draw one organic molecule, just one, make it G3P. It's here, it's glycolysis, it's hugely important. So think of this as a versatile 3-carbon organic chain. Does Dr. Pickard make you learn this structure? He should. I should go tell him, start putting this on test. G3P. It's 3 organic carbons stuck together. It's close to being half of a glucose. So if you want to build glucose and you get to this point, you're halfway there. If you want to break down glucose completely, you're halfway there. It is the same G3P. If G3P is in the stroma, so remember this is happening in the stroma, a G3P in the stroma is more likely to get built or to be used for anabolism and to build sugars than to be used as an energy source. But it's no different chemically than the glycolysis intermediate. And notice, all right, well, once we get to the point of glyceraldehyde 3-phosphate, this figure is correctly saying, like, oh, okay, that's what we need out of the Calvin cycle. The Calvin cycle didn't build glucose. That's a common misconception from, like, Bio 1, and I understand why they do that. The Calvin cycle literally builds glyceraldehyde 3-phosphate. And then there are other steps after that that take this and build it into bigger sugars. Most of the work that a plant has to do is just to get to this point. Build that size of a sugar or a 3-carbon compound. So, some of the glyceraldehyde 3-phosphate that's made during the Calvin cycle will leave or become a substrate to build sugar. Probably the most annoying part of the videos that you watched, it doesn't have anything to do with the video maker, but the concept that you have to have 3 CO2s come into this process if you're going to have one molecule leave the cycle. So this is a 3-carbon molecule. We're starting with a 1-carbon molecule. So when they go through and they do those multiplying steps, it takes 3 incoming carbons to allow one glyceraldehyde 3-phosphate to leave this cycle.
Why in the first video did they like multiply by 2 or something? Because then everything was like at 12.
Which one did you watch first?
The
Oh, I know what you're saying. Yeah, I remember now. The reason that they multiplied by, why did they multiply by 2
I
at
don't
the
know if it
start?
was by 2, but everything was 12.
Yeah.
Because they're focusing on this making glucose.
Oh, okay.
That's why.
Gotcha.
Yeah. So if we're saying that the real product of the Calvin cycle is G3P, it's a 3-carbon molecule. So you have to have 3 CO2s coming into the cycle to let 3 carbons leave. And you have to have 3 times as much ATP to do that, 3 times as much NADPH. Same for this step over here. That part is annoying, but true. Like, leave it out. You can't magically turn a CO2 into a G3P because there's only one carbon there. So if you care to imagine this the way it really works, there are millions of CO2s being fixed. There are millions of phosphoglycerates being formed. There are millions of G3Ps being formed. And a third of them will leave the cycle. Some of them will continue and go on and regenerate. So this side of the cycle, the purpose of it is to regenerate RUBPs to keep CO2 fixation going. We need enough RUBPs regenerated to still go pick up more CO2 and go fix more CO2.
So that's the main reason of why we need the 3 CO2s then, is so that we can regenerate the RUBP.
Yeah.
Not necessarily, like, because it would still make G3P even if it didn't have 3 CO2s, right?
Sets of 3.
But it wouldn't be able to keep in a cycle.
Yeah. If you don't, like if you think about this, we started with 5, we added 1. But the real product is a 3 carbon molecule, so it's the pools operating together. You were stretching. Yeah. It's the pools. So we need enough carbon to come in to get the G3P pool big enough that most of it can be used to regenerate the 5 carbon, but some of it now can leave and go participate in other cycles. So the question is, what do we need to know out of this? I want you to know that the literal product, the literal useful product of the Calvin cycle is glyceraldehyde 3-phosphate. I want you to know that the Calvin cycle is dependent on the ATP and NADPH being made in the light reactions. Their energy is used to help build these single carbons into organic molecules, to get them reactable enough. And you need to know that RUBP is regenerated during this cycle so that it can go and be reacted with CO2 by Rubisco. It happens in the stroma. It was worked out by Melvin Calvin cycle. Okay, so jumping ahead now to another picture. So remember, here's our symbol for Calvin cycle. CO2 comes in, triose phosphate leaves, like G3P. Triose, 3 carbons, ose for sugar, it's phosphorylated. Triose phosphate is the literal product. And that literal product is floating in the stroma. So remember, Calvin cycle is happening in the stroma, in the chloroplast. The machinery that a plant has to build bigger sugars are out in the cytosol. But G3P is being made in the chloroplast, in the stroma. So there is a particular protein that moves triose phosphates into the cytosol and swaps it for a free phosphate, which is cool. It's an exchanger protein. Both molecules are going in a needed direction. So we want to get sugar building blocks out into the cytosol. We need to get free phosphate going in here because there is ATP production going on in the chloroplast as well. So there's an exchange of protein that swaps those out. Once triose phosphate, which is a 3-carbon sugar, G3P, gets out into the cytosol, the plant can build it into other sugars. And if you're in cell, you might like be having a flashback over here, like, whoa, there's fructose 1,6-bisphosphate, glycolysis intermediate, yes. Fructose 6-phosphate, yes, glycolysis intermediate. But in the cytosol, the plant can build sugar or do glycolysis, either one. But the cytosol of a leaf mesophyll cell during the day will be operating to build sugar, not eat sugar, overall. And the sugar that plants are building is normally sucrose. So I want to end today by saying a little bit about sucrose. So in plants, sucrose is their preferred 6-carbon sugar that they use for fuel, more than glucose. What do plants mostly use glucose for? To build what?
Fruits.
Fruits have a lot of stuff in them. Well, they have sucrose and they have glucose and a lot of stuff in them, but that's a good cover the bases answer. What do plants do with glucose? They build these big chains of it for what? They make starch. They can make starch out of it, and they can make cellulose. So think about how much glucose they have to put into cell walls for cellulose. So they keep glucose around, and they also keep sucrose around. And sucrose is what they ship internally as a food source from place to place. It's still a 6-carbon sugar. It can be converted into glucose fairly easily through these steps that you don't need to know the details of, but we talk about photosynthesis in Bio 1, like it makes glucose. Well, it can, but it makes generally more sucrose for export than it does glucose. Yeah, one more minute here. So, all right, if we've made some sucrose in the cytoplasm, in the leaf, so leaf mesophils are cranking out sucrose if they're healthy, and the plant is going to ship sucrose, export it through the phloem to the rest of the plant to supply food for the plant. Because a lot of the plant tissues aren't photosynthesizing and they need food. They're getting it via shipment, so to speak, of sucrose from photosynthesizing leaves. I'm going to end there. We'll probably start on this same slide on Friday. And for Friday, you need to watch, there's 2 videos. There are 2 videos that are next in the list, and there are also a couple of short documents about Rubisco that I'd like you to read that I just put in there today. So that's for Friday. And Friday we'll be talking about photorespiration, or inappropriate action of Rubisco.